Let's start by reviewing the four main theorems of calculus that we've learned so far. Intermediate value theorem, extreme value theorem, Rolle's theorem, and mean value theorem. So there's some key things that we want to remember on each of these theorems. Now for each of them, I've actually written them out ahead of time. So you can always pause the video, copy down the theorem, and then we're going to go through the explanation of them. So on intermediate value theorem, the key word is that f of x is continuous on a closed interval a to b. So that means if we had a picture of it, that we have a continuous function, no holes, no asymptotes, nothing like that. So if it's continuous, you know, blah, 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 from a to b, so from some x value a to some x value b, from here to here, and there is a value k that's between f of a, which would be right here, this would be f of a, it's the y value with a, and f of b. So we have f of a is the y value with a, f of b is the y value with b. There is at least, so if we know a value k somewhere in here, somewhere in that realm, k. What intermediate value theorem says is that there's going to be an x value that has that k as a y. Somewhere that this c value has k as a y value. That's all it really says. It really just means we're going to pass through every y value on the way from a to b. The next one is the extreme value theorem. Extreme value theorem starts off the same. It's talking about, we have a continuous function on a closed interval. Now if it was on an open interval, we may not have extreme, like absolute maximums and minimums, because the graph could go on forever in both directions like a line. But if we have a closed interval, so let's see, I'm going to draw a picture. Okay, beautiful continuous function. And let's say we have a here. So that's where the graph we're talking about that it's starting at. And let's say b is here, and that's the end point of our graph. What it's saying is that there is going to be an absolute minimum and an absolute maximum somewhere on the graph. And those somewheres could occur at either the first endpoint, the last endpoint, or anywhere where our derivative is 0 or undefined. So notice here we have a derivative of 0, horizontal tangent line, and here we do too. So where are my absolute maxes and mins occurring, the highest and the lowest points? Well, actually, right here and right here are both absolute minimums. So in this picture, I have two absolute minimums. One's occurring at f of a, and one's occurring at this c value, that c value. So those are both absolute minimums. There's two. Now our maximum would be here. That's an absolute maximum. So it either occurs at endpoints or at relative mins and maxes. Makes sense. The next two theorems are very much related. These are talking about derivatives. The first one is really a specialized version of mean value theorem. Rolle's theorem says that if we have a continuous function and differentiable, notice the difference here. This one says it definitely has to be differentiable. If we have a continuous and differentiable function, And the key for this one is that f of A has to be the same height as f of B. So I'm just going to use, we're going to use something similar, and I'll make it back down. Okay, so if f of A and f of B are at the same height, so here's A, here's B. So f of A and f of B are at the same height. What it's saying is that at some point I had to turn around. I have to have a place somewhere where the derivative is 0. At least one time. In this case, I have this spot, I have this spot, and I have this spot. Now, it's kind of logical that we're gonna have some rolls if we start and end at the same place. But if we think about this in the context of mean value theorem, which we'll get to next, notice that if I found the slope between A and B, f of A, f of B, they have a horizontal line going between them, horizontal secant. So looking at mean value theorem says that if I have any function that's continuous and differentiable, so this time it could be any old function, let's see, and this time we're not considering that A and B are at the same height. So let's say A starts here, and for fun I'll make B be up here. So between here and here. What it's saying is that if I draw the secant line between A and B, secant line went through the 2 points, so I have a line like this. Mean value theorem says there's going to be at least one other place that has the same exact slope as that line. Well, if I look, I could draw that right here. I can also draw one right here, that all are parallel to this secant line. So mean value theorem just says that there's going to be a tangent line that has the same slope as the secant line. Well, Rolle's theorem is just a specialized version of that. The secant line has a slope of 0, so we must have a tangent line with a slope of 0. Very, very similar. Now let's look at some applications of these theorems and see which ones apply. So we have the rate at which water flows out of a pipe in gallons per hour. The table shows the rate as measured every 3 hours for a 24-hour period. Estimate, ooh, love that word. I know I'm going to have a secant line. Estimate the value of r prime of 5. So the rate of change of r at 5. Well, if I'm estimating it, that means I'm not going to find the actual slope, the instantaneous slope. I'm going to have to find the average slope. So r prime of 5 would be approximately, 5 is between 3 and 6, so r of 6 minus r of 3 over 6 minus 3. Okay, so r of 6 is 10.8 minus 10.4 over 3. That's 0.4 over 3. And it's positive. And this is gallons per hour per hour. So gallons per hour squared. Now, what does it mean in this context? Well, it's positive. So R prime of 5 is positive, so the rate at which the water flows out of the pipe is increasing at time equals 5. Find the average rate of change of R from 3 to 18. That's actually asking for a very similar thing. We're going to be taking R of 18 minus R of 3 over 18 minus 3. So R of 18 is 10.7. R of 3 is 10.4. 18 minus 3 is 12. And that is 0.3 over 12. And that is gallons per hour per hour. So gallons per hour squared. Is there such a time between the starting time, 0, and 24, such that the instantaneous rate of change would be 0? So for that to happen, R of t would have to be exactly the same at 2 of those places. So let's see if that happens. Well, for us to really make sure that happens, remember this is talking about a derivative. So we need to make sure R of t is continuous and differentiable. So they tell us that it's differentiable. So since R of t is differentiable, it is also continuous. Remember, it has to be continuous to be differentiable. So I've stated my theorem, or my conditions for my theorems, and now I want to think about which theorem applies. It's talking about a derivative, so that's not intermediate value, it's not extreme value, it's either mean value or Rolle's. Well, this one, Rolle's theorem applies. So I just have to find two in. Again, since Rolle's theorem applies, we have to have 2 endpoints that have the same y value. And if I look back, that's at 0 and at 24. F of 0 equals f of 24 at 9. They both equal 9.6. Therefore, there exists a value c on 0 to 24 such that R prime of t is 0. Notice we have to state our conditions first, and the two main conditions for Rolle's theorem is that differentiable and continuous, and that we have two y values, two outputs of our function that are exactly the same. Alright, so we have the total order and transportation cost C of X measured in dollars of bottles of Pepsi-Cola. X is the order size and number of bottles in hundreds. Okay, is there guaranteed a value R on the interval from 0 to 3 such that the average rate of change of cost is equal to C prime of R? Okay, so average rate of change would mean secant equaling an instantaneous, that's mean value theorem. So we need to see if we're continuous and differentiable between 0 and 3. But notice when x is 0, I'm dividing by 0 in this function. So since c of x is undefined at at x equals 0 actually. At x equals 0, it is not continuous. It is not continuous at x equals 0. Therefore, a value r cannot be guaranteed. Could there be one? Sure, but it's not guaranteed. We don't need to even look for it. Is there a value r between 3 and 6? So 3 and 6 are good. So I could take the derivative. It's continuous. So c of x is continuous on 3 to 6 and differentiable on 3 to 6. The next things we'd have to find, because it's asking to see if the instantaneous derivative is 0 somewhere, we need to see if c of 3 equals c of 6. So I would just go to my calculator and plug in 3 into that function for c and 6 and see if they're the same thing. And I'm going to go off to the side. C of 3 is 8333 point. Okay, so it's 8333.333, and so is 6. Rolle's theorem applies. And this would be a calculator-based problem. You would be able to go to your calculator and actually find it. C prime of r equals 0 when r equals 4.098. So you could be able to find that pretty easy on a calculator. For 3 to 9, what is the greatest cost? So remember there's a couple of things here. To find the greatest value, we're talking about an extreme, an absolute maximum. So we're good from 3 to 9. It is continuous. So we've already said it was continuous from 3 to 6, but I would say c of x is continuous on 3 to 9. So EVT applies. So we have to check a couple of things. We have to check our endpoints, and we have to check any extremes that we had in the middle, which we just found one. We need to check c of 3, c of 4.098, that was found in the last one, and c of 9. And this would be a calculator-based problem again. So this is going to be 8333. We found that earlier. This is 8213.67, 8611.11. So the greatest cost is for 900 bottles and is $8,611.11. I'm going to skip this example. It's very, very similar. And we're going to go to one where we're using a table. So in the table, we're given f of x, f prime of x, g of x, and g prime. And it says both are differentiable. So f and g are both differentiable. So I might make a note, f and g, and g are differentiable. And continuous. Once I know they're differentiable, I know they're continuous. So any rules are going to apply. And h of x is given by f of g. Our point is going to be h of 3, which means that's going to be f of g of 3. And then we're also going to have to find the slope, which is going to be h prime of 3. So let's think about the derivative. The derivative of the outside with the original just like it is times the derivative of the inside. Chain rule. So g of 3 is 4. G of 3 is 4, and then f of 4 is negative 1. So h of 3 is negative 7. So this is my point, my x and my y. To find the slope, h prime of 3. So g of 3 was 4, so now I need to find f prime of 4 times g prime of 3. F prime of 4 is 3. G prime of 3 is 2. So my slope is 6. So I'll get y plus 7 equals 6 times x minus 3. There's the equation of the tangent line. The next is asking for find the rate of change of h for the interval from 1 to 3. So rate of change over an interval means I need to find h of 3 minus h of 1 over 3 minus 1. We're finding the slope of that secant line. So the only thing I don't have is h of 1. So h of 1 is going to be f of 3 of 1 minus 6. G of 1 is 2. F of 2 is 9. So h of 1 is 3. So I've got h of 3 was negative 7 minus h of 1, which is 3, over 2. That's negative 10 over 2, negative 5. Explain why there must be a value of r for 1 to 3 such that h of r equals negative 2. Well, h of 3 was negative 7, and h of 1 is 3. Negative 2 lives between that, so h of 3 is less than negative 2, which is less than 3, oops, less than h of 1. Since f and g are continuous, h of x is continuous. Therefore, by IVT, there exists an R on 1 to 3 where h of r equals negative 2. Alright, explain why there's a value from 1 to 3 that h prime of c equals negative 5. Well, we just found that the rate of change from from 1 to 3, the secant line was negative 5. That means there is a slope where the derivative is negative 5. There's a slope of a tangent line. So since f and g are differentiable, h of x is differentiable, mean value theorem applies. There exists a value c such that h prime of c equals, and I'm going to go ahead and be very specific, h of 3 minus h of 1 over 3 minus 1 equals negative 5. Since we'd already found that earlier, I don't have to show all the work. I can just copy it down.